Changes in the spread of a process can lead to out-of-specification products. In this lesson, you will learn how to create a control chart for ranges to monitor the process spread. And hello again to this lesson, which essentially has 3 learning objectives. After this lesson, you should be familiar with the terms range and precision and understand why it is necessary to monitor the spread of a process. You should also be able to use a sample to calculate the range and the spread in the form of the standard deviation. Of course, the focus of this lesson is that you should be able to create a control chart yourself and calculate the warning and control limits. This lesson is divided into 3 chapters. In the first chapter, you get an overview of what the range is and how a change in the spread can lead to characteristics that are out of specification. In the second chapter, the range and the standard deviation of the process are calculated based on the data from a pre-series. And in the last chapter, the actual control chart is created and the warning and control limits are calculated. To be able to classify the range control chart in comparison to the other quality control charts, this picture shows the connection between the various characteristics and the control charts used. The different characteristics are shown on the left and the different control charts on the right. The quantitative characteristics, shown on the left, can be divided into 2 different categories. First, the variable characteristics. These are all characteristics that can be measured. They always have a value and a unit. Examples of this would be the length, hardness, weight, surface roughness, or tensile strength of a component. Second, there are the attributive characteristics. Those are all characteristics one can only count. But we don't want to go into detail about them here. On the right, we have the different control charts for variable characteristics with a white background. These are also called Shewhart charts, named after American Walter Andrew Shewhart. As you can see, there are 3 control charts for monitoring the process location and 2 control charts for monitoring the spread. The range chart is one of the spread charts. Let's start with the basics of range and spread and why it should be monitored. As a practical example, we take this tried and tested piston again. The product characteristic to be monitored is the nominal diameter of 60.1 mm. In one of the basic lessons, the difference between precision and accuracy was explained in detail. In short, precision is the degree to which results, when measured repeatedly, vary. The distribution of the measured values, shown on the left, has a small spread. This process is therefore more precise than the one on the right, which has a much greater spread. To describe the precision, one can, for example, determine the range of a process result. The range is calculated from the difference between the maximum and the minimum value and is particularly suitable for small sample sizes. A small range corresponds to a small spread of values, and a large range corresponds to a large spread of values. As can be seen on the right, increasing the range can result in the lower and/or upper specification limit being exceeded. These would be the measured values shown here in yellow. The distributions just shown on the histograms are based on concrete individual measured values. These individual measured values are shown in this value curve of a control chart. It can also be clearly seen here how the values in the first range scatter only slightly around an average value and are far from the specification limits. Various influences, can lead to an increase in the spread of the values. This can be seen on the far right. There, the spread of the values has increased so much that 3 values are outside the permissible specification. Because increasing process variation can lead to out-of-specification characteristics or products, the process spread should be monitored. Let's briefly review the meaning of the symbols in the formulas. Sigma is the standard deviation of the population, and sigma hat is the sample standard deviation. The d-factors are required to calculate the warning and control limits. These are taken from tables. The d-factors are calculated using the W distribution depending on the size of the sample and the chosen non-interference probability. To calculate the limits, the standard deviation of the population must be known. Since this is usually not known, it must be estimated as good as possible using a random sample. This random sample can be taken from an ongoing series production or from a pre-series. In this chapter, let's take a look at the results of such a pre-series and use the measurement results to calculate the ranges and the standard deviation. Several random samples were taken and the diameter of each part measured and the measurement results entered in the table. Then the values were entered into the control chart. This resulted in the value curve shown here. When calculating the warning and control limits, it is assumed that the values are approximately normally distributed. A visualization in the histogram and the envelope curve above it should be sufficient proof for this at this point. The range was calculated for the 5 individual values of a random sample and documented in the right-hand column. The mean value was then calculated from these ranges. Our bar has a value of 0.068 mm. Now the standard deviation must be calculated based on the same measured values. This can be done, for example, with MS Excel and the function stdev.s. However, there are other methods that can be used to estimate the standard deviation. 2 of these are shown on the right. If you don't have a computer to help you, you can also calculate the standard deviation manually using the range R and the value dn. Values for dn and an would then have to be taken from tables again. Now we come to the actual creation of the control chart and the calculation of the warning and control limits. The structure of an R chart is much like that of the other control charts. On the y-axis, however, is the scaling of the range. In the table for the measured values, the range is calculated and entered from the difference between the maximum and minimum value. The warning and control limits are also calculated for the usual 95 and 99% non-interference probabilities. In the first chapter, we calculated the standard deviation using the MS Excel function stdev.s and pointed out that there are alternative calculation methods that do not require a spreadsheet program or other specialized software. I would like to present such a method here, since the tables used to calculate the warning and control limits usually also contain values for these alternative methods. So, an alternative method of estimating the standard deviation can be done using the mean of the ranges. For this, you need the denominator dn, which depends on the sample size and can be found in tables. If we calculate the mean value of the ranges for the first 10 random samples, as shown here, we get a value of 0.068 mm. As has already been said several times, values for dn and the d factors are taken from tables that can be found in the relevant literature or on the internet. A small excerpt of such a table is reproduced on the left. For the sample size of 5 given in this example, one now extracts the values for dn and the d factors. This gives us everything we need to estimate the standard deviation. Inserted into the formula, a value of 0.029 mm is obtained for the standard deviation. This is rounded up to 0.03 mm. If you continue to insert the values for the standard deviation and the other factors from the table into the formulas for the upper and lower warning limit and for the upper and lower control limit, the values calculated here result. The values just calculated for the upper warning and control limits were drawn on the control chart. The lower limits are only indicated here. When these are so close to 0, these limits can be omitted altogether. The goal is to have as little spread as possible anyway. It therefore makes no sense to have a warning or control limit so close to 0. Here is a brief explanation of what these limits mean. The warning limits UWL and LWL are such that the range of a random sample will lie between these limits with a probability of 95%. For the control limits, this probability is 99%. For the reasons just explained, the lower limits have been removed in this control chart. The probability that the range of a sample exceeds the upper control limit is less than 1%. When such a rare event occurs, it is an indication that the process may be out of control. The cause must be identified and the process readjusted if necessary in order to reduce the spread again. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 4 most important key messages. The average chart monitors the centering of the distribution of data from the process. The range monitors the spread of the distribution. The non-interference probability for the control limits is 99%. A value outside the control limits indicates an out-of-control process. A readjustment might be necessary. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye.